In this video I'm going to talk about Eulerian cycles in graphs and the criterion when such a cycle exists. So definition: an Eulerian cycle in a graph is a closed walk, so it's actually not a cycle but a closed walk that passes through each edge exactly once. So like in general, by a cycle, in graph theory, we mean a cycle that doesn't have self-intersections. So a cycle cannot go through the same vertex multiple times, but a closed walk can. So that's basically the difference between a cycle and a closed walk. And so properly speaking, like we would need to call it Eulerian closed walk, but like it's already an established term to call it an Eulerian cycle. So whatever. So the main result is the Euler's theorem that says that so a graph has an Eulerian cycle if and only if, so this is in both directions, if and only if all of its vertices have even degrees. Okay, so let's consider the proof. So first let's prove in this direction. So suppose that it has an Eulerian cycle. Suppose it has Eulerian cycle. So then we consider this cycle. So there's some kind of this cycle, say something like this. So we notice that for this cycle to exist, so like when we go through this cycle, when we come to a vertex, we need to go away from this vertex by another edge, because the edges do not repeat. So like the Eulerian cycle, it passes through each edge exactly once. So when we come to a vertex, we must exit from this vertex. So the number of edges incident to this, like that are part of this cycle when we go through a vertex is even. So we so each visit, let's put it this way, each visit to a vertex, each visit to a vertex contributes two edges incident to this vertex. Contributes two edges to the degree of this, contributes two edges to the degree of this vertex, to its degree. So we might visit this vertex multiple times. So for example, this vertex is visited twice. So we pass here and here. So we contribute 2 to its degree, and then when we go here, so we contribute another 2 to its degree. So each visit to a vertex contributes 2 edges to its degree, or adds 2 edges to its degree, and like whatever is the number of times that we visit the vertex, like in total we would have so the degree of, so basically it follows from this that the degree of each vertex. So the degree of v, of vertex v, would be equal to the number of visits, twice the number of visits, 2 multiplied by the number of visits, 2 multiplied by the number of visits the Eulerian cycle visits this vertex. So from this we conclude that degree of v is even, because it's like 2 multiplied by some number. So basically this concludes the proof of this direction. So now let's consider the proof in the other direction. So suppose that for every vertex v, the degree of v is even. So now what we are going to do is we are going to construct the Eulerian cycle. So first we start from an arbitrary vertex, and we go like wherever we go. So we go by any edge, we come here. So when we come to a vertex, we always have a pass out, because the degree is even. When we come here, like by an edge, so this is one edge, there always must be another edge. So when we already visited this vertex, so after some time we come again to this vertex. So these edges that are already visited, they are already have an even number. So because the total degree of this vertex is even, so this edge by which we came to this vertex is like when we add it, it would be an odd number. So therefore we must have again an exit, because the total degree is even. So we never get to an impasse. So let's write it this way: we always have an exit from a vertex, from any vertex, except the first one. So because the first one is a special vertex, like we started this path here. So because the number of edges in the graph is finite, edges and vertices, so sooner or later we must return to the original vertex. So we must return to the original vertex, like after a finite number of steps. Finite number of steps. We must return to the original vertex. So this would be a closed walk, but it might not be an Eulerian cycle, because we might not visit some edges at all. So it is a closed walk. It is a closed walk. So now, so we already have some closed walk. Let's draw it this way. So now what we do is, like, if there are still edges not visited, yeah. So I forget in the theorem statement that the graph must be connected. Yeah, this is an error. So a connected graph. Okay. Yeah, that's important. So a connected graph has an Eulerian cycle if and only if all of its vertices have even degrees. Yeah. So yeah, because this disconnected graph, it can't have an Eulerian cycle. So it is a closed walk, and we know that it is connected. That's where we use the connectedness. So we know that it is connected. Therefore, like if there are still edges not visited, let's say this is an unvisited edge, and because the graph is connected, then there is some path from this edge to this cycle, to some vertex of this cycle. So like there is some kind of path here because the graph is connected. So then basically what we do is we start from this vertex, and we go by, so it means that there is an edge from this closed walk, already existing closed walk, that passes outside by an edge that is not yet visited. So there is an unvisited edge going out of this closed walk, like this. So we go by this. We go by this edge, and we basically start another closed walk, another walk. But we treat still this the first closed walk still as visited. So all edges of this closed walk we treat as visited. So we cannot visit them again. So we start by this. We go again like. We construct again a closed walk, just a walk. We construct again a walk when we arrived at the vertex. Because of the even degree, we must have an exit again. So we go somewhere, but after a finite number of steps, again, we must return to the original vertex, because it's the only vertex that has an odd number of edges already visited. So we must return here. So basically what we do then, so let me remove this. So basically we attach this another closed walk to the first one. So basically we treat it as like we merged them together. So let's say this is the vertex. So we go here, then we go here by this closed walk, and then we go here. So this is the same vertex. I just draw it separately to demonstrate how we walk. So we walk this way, and this way. So yeah, so basically we walk here, then we walk here, and return here, and then we walk here. So we merge these two closed walk together, and we obtain a single large closed walk. Right? So if there are still some unvisited edges in the graph, then we repeat the same procedure. So then again, by connectedness, there must be an unvisited edge going from the from this closed walk. Then we go from here, obtain another closed walk, and merge it together to the original one, and repeat the same procedure until there are no unvisited edges. And this would be when we arrived at this point, this would be an Eulerian cycle. Yeah, so basically that concludes the proof.